So taking a minute here to talk about how I built this circuit. This is from exam 2, problem number 1. And basically what we're doing is we're building a countdown clock. Design a counter that decrements from 3 to 0. So let me reset this. And I'll cycle my clock here, and as you can see this is set to 1, 1, which is 3. The countdown stops at 0, so let me turn off reset here, and let me turn on backward. Okay, and you can ignore these values here since they're not attached. So now I'm going to run my clock, and we're now down at 2, 1, 0. And what I'm doing is I'm watching these values here or these values up here. So I'll reset it. Reset, we're now back at 1, 1 because both of those are red. I'll turn off reset, and we'll watch these two up here as they change. So we're now at 2, 1, 0. Okay, reset. All right, now the counter can be paused, which is this button here. So we disable backward. And now if we turn off reset and we hit our clock again, nothing happens. And that'll happen through all the values. So we turn backward on, we cycle our clock once, we turn backward off, and we cycle our clock, nothing happens. On again, cycle our clock, off again, cycle our clock, on again, cycle our clock, and now we're at 0, 0. And it doesn't matter how many times we cycle the clock on 0, 0, whether it's in backwards or pause mode, it'll always stay at 0. Okay, so the counter can be paused. Use 2 different flip-flops, and I did. So this flip-flop here is the JK, and this one down here is the D. I apologize, they're not marked. Could have used a T here just as easily. LEDs to indicate, I did what number that we were at, and he also wanted a LED to indicate whether or not we had paused the count. And you'd probably want another LED of a different color to indicate whether or not you're actually counting down. So you could drop another line off here, blah, blah, blah. Okay. And then use a reset circuit, which is this right here. So let's let me pull in this into the viewing range here. And this is the state diagram that I used. So we start at 1, 1, and as long as our backward counter is set to 1, we go back. We go back again, on each clock cycle, and if we are pausing, which is x equals 0, see here, so then we just cycle, and it doesn't matter whether or not x is 0 or 1 when we reach 0, 0, we just want to continuously stay there. When we do a reset, it doesn't matter what value we're at, we'll always come back to here, so that's why these are question marks. They could be x's, just it doesn't matter. Wherever we are within this diagram, we always come back here. And I use this version of the diagram because it's a little cleaner for me to see since I have dyslexia. All right. So the next thing you want to do, or that I did, is I built a state table here. So let me bring this back down into the viewing range. So I focused on my current values of A and B, and then whether or not I was, apologize, that should say backward, my value of x and whether or not I was counting down or paused. So 1 is, again, counting down, and 0 is paused. And then these are the states that A and B will equal after this operation is performed. So what I chose to do is I chose to create A and B here. with this logic. Now this adds in a little bit of time, but it allows you to confirm that you're getting A and B the right values. So if we reset this, and I'm going to put this back and turn it on. So reset. Okay, now I'm going to turn reset off. So our A and B values for the next round, next clock cycle, should be 1, 0, because we're starting at 1, 1. So if I cycle, that's correct. We came to 1, 0. And now, since we're at 1, 0, we do the math again, and our next one should be 0, 1, which it is. So we cycle. And now, since we're at 0, 1, our next value should be 0, 0. And there we go. We're now at 0, 0. Okay? So that's what that logic meant. From there, from that set of tables, I then did specifically k-maps for those two. So here's my k-map for going backward, and my AB values and what I should be getting. So this is my equation for that. And then here's going backwards and my state table for, or my k-map state table for B, and what values I should get for that. Okay. Now, then using that information, I was able to come down and build this diagram here and confirm that I actually was getting the values when I went back to this graph here, or this circuit here. So I built out this section here, and then I built out this section here, and just tested it to make sure that it matched what I got here. If it didn't match, then I iteratively went back up through all of this material here and said, what did I get wrong? If I wasn't getting A and B, next A and B values correctly, then something in my logic was wrong, obviously. Okay, moving on. So the next part of this puzzle then is doing the state table for, let's see if I can get this in the viewing range, the J state table. So we have the state of A and B, the initial states of A and B, which are going to be these values over here. So this is A and B here, and then they're being fed in here and here, and they should be coming out here. So we have A naught, B naught here, and then we have what A naught should be. And we're really only interested in the J state table because that's the only one that has these state values that have to change. Now, I don't use the don't cares. It's a preference on my part. I just use the ones and zeros because I know that, and I'll show it. Let's see if I can find it here real quick here. So here's the don't cares. If you were to say you're going from Q naught to Q1 and you're going 0, 0 to 0, 0, or from 0 to 0, or 0 to 1, or 1 to 0, or 1 to 1, well then you're going to use, you don't care whatever K is, and this is 0, and so these are the values here. It's either going to be QT or 0, so you're going to put a 0 here. It can be a don't care. If you put it to 0 like I did, you're not losing anything, in my opinion. Maybe Dr. Song or Professor Song will disagree on why the don't care should be there. I'm not running into any problems at the moment. So these are my states for every transition. So I'm just looking at the transition between this A and this A. So if it's staying 0, then I'm putting that in. This could be an X, or that could be a 1. Let's see. No, that could be, that has to be a 0, so that could be an X. But that's how that works. So you're putting the values of the JK in here. And then you come down and you do your K-maps for the JK, and it's relatively straightforward. The only thing I screwed up in doing these maps initially was this column right here. It has to match the column that you started with way at the top here. I accidentally inverted it so that I had zeros and then ones, and that messed up the entire circuit. So once I got that straightened out and built these up, this is the equations that I came up with. So now let's go back to our circuit here, and you can see the values of J and K being assigned here. And I just put in my labels to make life easier for myself. So here's these four, and then my ORs, and I'm using lights to determine whether or not the JK are actually being assigned properly. Even before I went and did any of this. So once I know that J and K are being assigned properly by testing it with these switches here, then I went in and built this here even without the reset to make sure that it was populating properly. So I could, do this and have the clock running, and I would see the values populate, not even having A and B connected back into A and B. Okay, so the next piece of the puzzle then is actually adding in your reset. So let me bring my document back here, and we'll scroll up to my reset work. So here's my reset work. So my reset table takes in the current state of JK, and that's really the puzzle we're fighting with on this circuit diagram, is this piece right here. The logic here for D is relatively simple. We're going to set it high to 1 because we want this to be 1 on reset. So regardless of what this value is, this is always going to be 1 on our reset. So when we do a reset of 1, it's going high. It's the logic here, when this goes to 1, what happens to these values, because in order to get JK to be J1 and K0, we have to look at what states are coming in from our JK logic here. So for that, we look at all of the states here, whether or not the reset is 1 or the reset is 0. And then we look at what state we want JK to be in when we're done. So this is 1, this is 0. And then here, where the reset is 0, we actually want the states to match. We want it to just pass through. So now we build out our JK map, which is this K map. And so that gives us basically RST and J, which is this column here. And then we have these two values right here. RSTK. Oh, yeah, RST and K. It's not, there's no plus in there. That's what's throwing me off. So I'll go back over here, and we can see that we've got our J value being an OR between the RST and the J value, and then we can see that this is a RST not with our K value, and that determines whether or not we get a K coming in. Yeah, which doesn't match my K map. Apologize. Okay, so after that, then I'm using the JK device and the D device, D flip-flop, JK flip-flop and D flip-flop provided by CircuitVerse. And that's pretty much about it. So, hope you enjoyed, and hope you learned something.